right, folks. Today we're going to talk about 7B combining probabilities. So let's get started. Let me get full screened here. Okay, so the first combination of probability is going to be an AND probability for independent events. So two events are considered independent if the outcome of one does not affect the probability of the other. And if you want to know the probability of two independent events occurring together, you can use this formula here, which is that P of A and B occurring is equal to probability of A times probability of B. And it says this can be extended to any number of independent events. So if you had a third event C and you knew it was independent of A and B, so knowing their outcomes doesn't affect C, all this means is that we can extend that formula this way, right? So probability of A times probability of B times probability of C, and so on. All right, so let's do a quick example. What's the probability of rolling 3 6s in a row with a single die? Well, we know that the probability of rolling a 6 is just 1 out of 6 for a 6-sided die. So what they're asking is 3 6s in a row. So probability of 6 and 6 and 6. And since the outcome of one roll will not impact the outcomes of the following rolls, they are considered independent. All I have to do is then multiply together 1 6 times 1 6 times 1 6, which is just their individual probabilities. And that comes to 1 out of 216. And there's our answer. All right, so moving on. And probability for dependent events. So dependent events are two events where the outcome of one does affect the probability of the other event. And so that slightly alters our probability formula for the probability of A and B occurring together to being the probability of A times the probability of B occurring given that A has occurred. So slightly different. So the easiest way to understand this formula, I think, is through the next example. So a 3-person jury must be selected at random from a pool that has 6 men and 6 women. What's the probability of selecting an all-male jury? So we want to know the probability of getting a man and a man and a man. Well, these are not independent events, and the reason is once one person is selected, they're no longer in the jury pool. So that has fundamentally changed the total number of jurors to be selected from. So here's what we'll do. The formula becomes the probability of selecting a man times the probability of selecting a man given that the first person selected was a man. And so that line generally means given that. And then times the probability of selecting a man given that the first and second jurors selected were male. All right, so let's start with the first one. What's the probability that the first person selected is male? Well, there's a total of 12 people in the jury pool, and there's 6 men, so probability that the first one selected is male is 6 out of 12. So now we assume that the first one selected was male. And so if the first person selected was male, there are only 11 people left to be selected from, and there are only 5 males. So we're going to multiply that by 5 over 11 times, and now we're looking at this, the probability that the third person selected is male, given that the first 2 selected were male. So now, if the first 2 selected were male, there's only 10 people remaining to be selected from, and there's only 4 males remaining because the first 2 selected were male. So now all we have to do is multiply this out, and that's going to give us our final probability that all three were male. So do that. Let's go to my calculator. We'll just enter that in verbatim. So 6 out of 12 times 5 over 11 times 4 over 10. All right, and that gives me about 0.09. So I'm just going to use my approximation and say that that's about 0.09 or 9% chance that that would happen randomly. All right, so we're going to jump to non-overlapping events and either or probabilities here. So two events are non-overlapping if they cannot occur together. So give an example here of flipping a coin. Heads and tails are non-overlapping because you flip a coin, it's either heads or tails, and they can't happen together. For that, the probability formula is just going to be probability that A or B occurs is equal to probability of A plus the probability of B. And again, this can be extended to any number of non-overlapping events. So let's apply that in an example. Suppose you roll a single die, what's the probability of rolling a 2 or a 3? So probability of 2 or 3. You can't roll both at the same time, so they are non-overlapping. So the probability of rolling a 2 is just 1 out of 6, if it's a 6-sided die. And then we would add to that the probability of rolling a 3, which is also 1 out of 6. So this comes out to 2 out of 6, which we can reduce to 1/3. And that's it. All right, so what about events that are overlapping? They can occur at the same time, like picking a queen or a club in a deck of cards. Well, here we have all of our clubs. Here we have all of our queens, and we note that there is a queen that is also a club. So those two events, queens and clubs, do overlap with one card. So in that case, if we were to just add the individual probabilities, we would be double counting the queen of clubs. So that would be calculated in the probability of queens and the probability of clubs. And we only want to count that probability once. So what we're going to then do is subtract off the probability of A and B, or in this case, the probability of selecting a queen that is a club, since that got double counted. All right, so let's do an example of that. What's the probability in a standard shuffled deck of cards you will draw a 5 or a spade? So remember, we would have our 5s, and here we would have our spades, and the overlap would be the 5 of spades. All right, so probability of 5 or spade. All right, so remember that in a deck of cards, there are 52 cards total, and there are 4 5s. So the probability of selecting a 5 is 4 out of 52. Plus, there are 13 spades, 13 of each suit, so the probability of selecting a spade is 13 out of 52. But we double counted the 5 of spades in those probabilities, so we're going to subtract off the probability of selecting a 5 of spades, and there's only one of those, so minus 1 out of 52. All right, so 4 plus 13 is 17, minus 1 is 16, so we get 16 out of 52, or what is that? Divide by 2, 8 out of 26, or reducing it further, 4 out of 13. I think that's as far as we can go. All right. All right, so let's talk about the at least once rule for independent events. So suppose the probability of event A occurring in one trial is P of A. If all trials are independent, then the probability that the event A occurs at least once in n trials is shown below. So probability of at least one event A in n trials is 1 minus the probability that no events A in n trials, which is equal to 1 minus the probability of no A in one trial to the nth power. It's a little bit more of a complex rule, but I think it'll be easier to understand once we give it some context in this example. So use the at least once rule to find the probability of at least one head when you toss 3 coins. So probability of at least one H in 3 tosses. So that's going to be equal to, we're going to kind of use the complement rule, 1 minus the probability of no H, no heads in 3 tosses. All right, so what is the probability just of not getting heads? Just in a single toss. Well, that's the same as saying there's only 2 outcomes, so that's the same as saying the probability of getting tails, right? Which is just 1 out of 2. So in 3 tosses, since flipping a coin, they're independent trials, that's going to be 1 minus 1 out of 2 times 1 out of 2 times 1 out of 2, which is 1 minus 1 out of 2 to the third, which is where that formula comes from, right? That's where the to the nth power comes from. N is the number of trials. In this case, 3 tosses, so 3 trials. And that's where my exponent comes from. All right, so let's just simplify this. So that's 1 minus an eighth. 1/2 to the third is an eighth. So that's 7 out of 8. There's my final answer. All right, so last example here. I'm going to add some real life context, not just coin flipping. All right, you purchase 10 lottery tickets for which the probability of winning some type of prize on a single ticket is 1 in 10. I'm just going to make a note of that. So probability of winning on a single ticket is 1 in 10. What's the probability you will have at least one winning ticket among the 10 tickets? So probability of at least one W out of 10 tickets. All right, so going back to our formula, that's going to be 1 minus the probability of no winning tickets out of 10, which is going to be 1 minus the probability, of no winning tickets, the probability of no winning ticket to the 10th power, because there are 10 trials. So first thing we want to know is what's the probability of not winning on a single ticket? Well, if the probability of winning on a single ticket is 1/10, then the probability of losing on a ticket is 9/10, right? And so this becomes equivalently 1 minus probability of no wins to the 10th power, which is going to be 1 minus 9 out of 10 to the 10th power. We're going to go to the calculator and approximate this one. All right, we'll just enter it as is, 1 minus 9 out of 10 I'm just going to raise that to the 10th. We get about 0.65. So about 0.65, or a 65% chance that if you buy 10 lottery tickets where the chance of winning is 1 in 10, at least one of them will be a winning lottery ticket. So there's your associated problem set. As always, I advise doing these, and I'll post the answers, but what you'll be turning in for your homework is the open note quiz.